If you've ever stared up at the night sky and felt your brain quietly whisper, "Hey, where does all of that end?" Congratulations, you've asked one of the hardest questions in all of science. It's the type of question that makes professional cosmologists roll their chairs away from their computers, stretch their backs, and think, well, here we go again. Because asking what lies beyond the edge of the universe is like asking what's north of the North Pole. It feels like it should make sense. It sounds like a reasonable question. But the more you poke at it, the more it slips through your fingers. Humans evolved to understand things like trees, rivers, seasonal changes, and why your neighbor keeps mowing the lawn at 6 a.m. We did not evolve to understand the geometry of space-time, the nature of cosmic inflation, or the behavior of quantum fields in a vacuum. So, when we ask, what's beyond everything, we are using instincts built for life on Earth to understand something that doesn't behave like anything on Earth at all. And yet, here we are, trying anyway. That's the best part of being human. Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. And wherever you are, maybe lying in bed, settling into the night, or just looking for a moment of calm, I hope this time feels peaceful. I hope your mind can soften, your breathing can slow, and your body can rest. This video is a journey through the deepest ideas in modern cosmology, but presented in a way that doesn't require a physics degree or a tolerance for equations that look like ancient spells. Instead, we'll use stories, analogies, and everyday experiences to explore the most mind-bending ideas about what the universe is, where it came from, and whether it even could have an edge. Thank you for being here. Now, we'll start with the hardest part, the beginning. Before the Big Bang. Let's clear up one thing immediately. The Big Bang was not an explosion in space. It was an expansion of space. If you imagine the universe as a loaf of raisin bread rising in the oven, the raisins aren't blasting outward from a central point. They're being carried apart because the dough is stretching everywhere at once. There's no center of the loaf where it all began. Every part of the dough participated in the rising process. But the real twist is this. The Big Bang wasn't just the start of space, it was also the start of time. That means asking, what happened before the Big Bang is tricky, because before might not exist in the way we understand it. Analogy: trying to go south from Antarctica. Imagine standing directly on the South Pole. You take a small step forward. Did you go farther south? No, you moved north because every direction from the South Pole leads away from it. South stops being meaningful. In the same way, physicists believe before the Big Bang may not be meaningful. Time itself, seconds, minutes, hours, years, may have been born along with the universe. Time didn't exist, and then suddenly start ticking. Instead, time unfolded from a state where the concept simply didn't apply. But didn't something have to exist first? This is where both physics and your brain begin to sweat. At extremely early moments, far earlier than even a trillionth of a second after the Big Bang, the known laws of physics stop working. Classical general relativity, Einstein's theory of gravity, describes big cosmic things beautifully. Quantum mechanics describes tiny things beautifully. But put them together, in a moment when the universe is extremely small and extremely dense, and you get theoretical chaos. Physicists call this the Planck era, and it is essentially the universe's unphotographed baby photos. Everything is blurry, and no theory we currently have can describe it with confidence. That's why the phrase "before the Big Bang" belongs to a category of questions that science knows is important, but currently can't answer with certainty. Possible answers. Here are the leading scientific possibilities for what before could have been. 1. The universe emerged from a quantum vacuum fluctuation. In quantum physics, empty space is not really empty. It seethes with temporary particles that appear and disappear so quickly that you don't notice them. The idea is that the entire universe may have been such a fluctuation, except one that didn't disappear. It's a bold thought. The universe didn't come from nothing. It came from the quantum structure of nothing. 2. There was a previous universe. Some cosmologists believe in a cyclic or bouncing universe. In this scenario, the universe expands, slows down, contracts, and then, after reaching extremely high density, bounces into a new expansion phase. In this view, the Big Bang wasn't the start of reality, only the start of our current cycle. We'll explore this idea more deeply in later parts. 3. Time existed before the Big Bang, but differently. Another possibility is that time is like a warped fabric. It may have existed before the Big Bang, but under such strange physical conditions that our usual concepts of time don't apply. You wouldn't have clocks, or hours, or events happening one after another. You might instead have had a static quantum state that gelled into the dynamic universe we experience today. 4. The multiverse existed first, and we budded off from it. This idea suggests our universe might be one bubble in a much larger cosmic froth. The Big Bang might represent not the birth of everything, but the moment when our bubble separated from a larger, eternally inflating background. If this is true, then before the Big Bang is simply elsewhere, another bubble universe, or the inflating medium that spawns new universes endlessly. 5. The Big Bang was a beginning with no before. This is the idea Stephen Hawking famously supported. In his model, time behaves like a four-dimensional sphere. Just as a sphere has no edge, time has no before. It simply bends smoothly into the beginning. Trying to go before the Big Bang is like trying to walk northwest from the North Pole. You can't. The geometry isn't built for it. So, what does this have to do with the edge of the universe? Everything. Understanding the beginning of the universe is essential for understanding whether an edge could exist at all. If space and time themselves began at the Big Bang, not inside something, not from somewhere else, then the universe is not expanding into anything. It's expanding by creating more space between things that already exist inside it. That means the very concept of an edge may not make sense. There isn't a wall you could reach, or a border where space stops. Space doesn't have a container. It's more like a mathematical structure that stretches and evolves on its own. This is where your brain usually says, "Okay, but what's outside that structure?" And physics replies, "There might not be an outside. Space-time could be all there is." The next part will explore that directly. Is nothing actually alive? Why the universe doesn't have an edge. The expansion of space and why it confuses everyone. If you've ever sat quietly and wondered, what is outside the universe? You're not alone. Almost everyone who has ever thought deeply about astronomy eventually hits this same mental wall. Even Albert Einstein admitted that he struggled to picture what it means for space to have no boundary. And Einstein was pretty good at thinking. To answer the question of what's beyond everything, we need to understand two big, slippery concepts. 1. What is nothing in physics? 2. Why space doesn't have an edge like a room or a box. These ideas connect directly, and once you see how, the universe becomes a lot less confusing, and a lot stranger. Let's start with this strange idea. Nature's big secret. Nothing isn't nothing. When most people imagine nothing, they imagine a blank, empty void. A big, cosmic zero. But that version of nothingness is more of a philosophical idea than a physical one. In physics, nothing is surprisingly complicated. The vacuum, the emptiest thing in nature, is not a blank space where nothing happens. It's more like a churning sea of invisible activity. Quantum fields cover all of space, even when no particles are present, and these fields never truly sit still. Quantum fluctuations, the restless vacuum. Imagine the universe as resting on an ocean that never becomes perfectly calm. Even when the surface looks smooth, tiny ripples are constantly forming and disappearing. They pop up, merge, fade away, and then return in different patterns. This is quantum fluctuation. The idea that empty space is alive with temporary particles that appear, exist for a fraction of a second, and vanish again. Nothingness, in physics, is not a silent void. It hums with potential. It's like the universe's engine idles in the background, even when nothing is happening. This idea, that the vacuum isn't truly empty, leads to one of the biggest questions in cosmology. Could the entire universe have emerged from one of these vacuum fluctuations? In other words, could everything, galaxies, stars, planets, even you, be the long-term side effect of a tiny quantum twitch? It sounds ridiculous, but it's one of the leading scientific explanations for the Big Bang. Before we go further, keep this in mind. What we call nothing often behaves more like almost everything waiting to happen. The universe doesn't have an edge. The way a box does one of the hardest concepts in cosmology is that space can be finite yet have no boundary. This is where analogies become essential, because our everyday experience doesn't prepare us for this. A room has walls. A planet has a surface. A garden has a fence. Everything we know has edges, but the universe is not in anything, so there's nothing to press against. Analogy 1. The surface of Earth. Imagine an ant walking across Earth. If the ant had never flown into space and had no concept of three-dimensional spheres, it might think the world just goes on and on. But if the ant kept walking, it would eventually return to the starting point without ever encountering an edge. The surface of Earth is finite but unbounded. You can travel endlessly without falling off, but that doesn't mean Earth is infinite. Now, apply this idea to three-dimensional space, not just Earth's two-dimensional surface. Space could curve back on itself the same way the Earth's surface does, just in a higher dimension. You could theoretically travel forever in a straight line and eventually loop around to where you started. No edge, no wall, nothing to fall off, just a smooth, continuous structure. Analogy 2. A video game world. In some older video games, when you walk off the right side of the screen, you reappear on the left. The world wraps around itself. There's no boundary in the game world. It loops. Space might behave similarly, just far more sophisticated and in more dimensions. So, if there's no edge, why does the universe expand? Here's another headache-inducing idea. The universe is expanding, but it's not expanding into anything. This is the part where people usually squint at the screen. Analogy. A stretching rubber sheet. Imagine a rubber sheet with dots drawn on it. If you stretch the sheet in all directions at once, every dot moves away from every other dot. No part of the sheet is the center of expansion. The sheet doesn't expand into another space. It simply stretches. Space behaves the same way. Galaxies aren't flying through space. Space itself is growing between them, and this expansion happens everywhere, not from a central point. No explosion, no center. The Big Bang wasn't like fireworks or a bomb where matter spreads into empty surroundings. It happened everywhere at once, because space didn't exist before the Big Bang. There was no location for it to explode into. This is why the question, what's the universe expanding into, is a little like asking, what's the edge of a map that has no edges? The map itself is the thing that's growing. So, why can't we see the whole universe? When we talk about the edge of the universe, we're usually mixing two concepts. 1. The universe itself. 2. The observable universe. The observable universe is the region we can see from Earth, limited by the speed of light and cosmic expansion. It's a bubble centered on us, and every observer has their own bubble. This bubble currently has a radius of about 46 billion light-years, but the actual universe could be much larger than the observable bubble, potentially infinite, a closed shape with no boundary, a tiny part of a bigger multiverse, something we don't yet have the math to describe. The important thing is this: the observable universe is not the entire universe. It's just the part we have access to. Imagine you're standing in the middle of a foggy field at night. You can only see the patch of ground illuminated by your flashlight. That patch is your observable universe. The rest of the field, the parts the flashlight doesn't reach, is still there, but you can't perceive it. We are cosmic hikers with a flashlight that reaches only 46 billion light-years. And the fog around us? That's the speed of light and the expansion of space limiting what we can observe. Now we can answer a crucial question. What is beyond the observable universe? Short answer: more universe. But what that more looks like is still unknown. Possibilities include more galaxies identical to ours, regions with different physics, an infinite pattern that repeats forever, a finite universe curving back on itself, other universes entirely. We'll explore these possibilities in later parts. Before that, we have one more concept to understand: the misleading idea that space could end. People imagine the universe having an edge like the wall of a room, the end of a road, or the game over boundary in a video game. But in general relativity, an edge makes no sense unless something is physically cutting space off. The universe doesn't seem to behave that way. Space is not a substance that needs a supporting structure. It's a geometric property, a mathematical object built from distances, angles, curvature, and energy. There is no outside, because outside is a spatial concept, and space is the thing we're defining. This is hard to wrap your head around because our brains evolved in a world full of edges. Trees, cliffs, rivers, and geographical borders. Everywhere we look, things end. But space is not like the things inside it. It has no boundary. It doesn't need one. It's not expanding into anything. It simply exists and changes over time. That brings us naturally to what comes next. At this point, we've established two huge ideas. One, the universe probably doesn't have an edge. Two, our ability to see the universe does. This distinction is so important that cosmologists sometimes joke that half of their career is explaining this difference, and the other half is arguing about what it means. So let's talk about the region we can see, the observable universe, and then slowly peel back the layers to explore what might lie beyond it. The observable universe, a bubble defined by light. Imagine standing in the middle of a dark lake at night with a lantern. The lantern's glow creates a circle of visibility around you. Beyond that circle is more lake, but you can't see it. Not because it isn't there, but simply because the light hasn't reached that far. The observable universe works exactly like that, except in reverse. It's not that our light hasn't reached the universe. It's that the light from distant regions hasn't had time to reach us. Light is fast, but not infinitely fast, and the universe has only existed for about 13.8 billion years. Because space is expanding, the actual radius of the observable universe is much larger than 13.8 billion light-years, about 46.5 billion light-years in every direction. That means we live inside a spherical bubble of what we are physically capable of detecting. Every observer in the universe has their own bubble. These bubbles overlap but are not identical. In other words, the observable universe is a personal horizon, defined by where light has managed to reach since the Big Bang. It's a cosmic bubble with a built-in blindfold. The blindfold, why we can never see beyond a certain distance. There are two big reasons we simply can't observe everything that exists. Reason one, the finite age of the universe. The universe hasn't been around forever. Because light takes time to travel, we can only see events whose light has had enough time to reach us. You can think of this like hearing thunder after lightning strikes far away. If the storm is close, the thunder reaches you within seconds. If the storm is extremely far away, the sound may never reach you at all. Light behaves the same way, but the distances are unimaginably larger. Reason 2, the expansion of space. Even if a distant galaxy emitted light toward us billions of years ago, space has been expanding during the entire journey. The farther the light travels, the more space stretches beneath it, slowing its arrival. Some galaxies are receding from us faster than the speed of light. Not because they're moving through space fast, but because space itself is expanding so rapidly that it carries them away faster than light can close the gap. This is allowed under general relativity. Light can't catch up. This creates a limit on what we'll ever be able to see. So yes, the universe may be infinite, but our vision is not. We live in a bubble defined by physics, not by the universe itself. The edge of the observable universe is not the edge of space. People sometimes imagine that at the boundary of the observable universe, there's some sort of cosmic brick wall or a shimmering veil of fog. But that edge is simply the limit of the data available to us. Think of it like trying to watch a movie when the internet is slow. The part you've downloaded is the observable universe. Everything ahead of that point exists, but the information hasn't reached you yet. The universe doesn't fade out into non-existence. It continues. We just can't see past a certain distance because the universe is young, and space is expanding faster than light can outrun. So the edge of what we can observe is not a physical thing. It's simply the limit of causality, meaning the limit of where information has had enough time to reach our eyes. How observation works like a time machine. Every time we look into space, we are looking into the past. The moon, 1.3 seconds ago. The sun, 8 minutes ago. Andromeda galaxy, 2.5 million years ago. The most distant galaxy currently detected, 13.4 billion years ago. Cosmic microwave background radiation, 13.8 billion years ago. This means that the farther out we look, the younger the universe appears. Eventually, we hit a wall. Not a physical wall, but a temporal one. We see the universe not as it is now, but as it was shortly after its birth. Beyond that point, the universe was so hot and dense that light couldn't travel freely yet. Instead of stars and galaxies, what we detect is a faint microwave glow, the afterglow of the Big Bang. This is called the cosmic microwave background, or CMB. It forms the oldest photograph the universe has allowed us to take. But beyond that photograph lies a period we cannot observe directly. It's like trying to look at the first 2 chapters of a book when the pages have melted together. So, what's beyond our observable bubble? This is where things get interesting. Cosmologists agree on one thing. There is more universe out there. Maybe a lot more. We know this because nothing in physics suggests that space suddenly stops where our telescopes can no longer see. In fact, all available evidence suggests the opposite, that the universe continues with the same large-scale structure far beyond our horizon. Here are the main possibilities for what lies outside our cosmic bubble. Possibility 1. More of the same. The simplest explanation is that beyond what we can observe, the universe continues more or less as it does here. Galaxies, clusters, voids, dark matter, dark energy. If the universe is flat on the largest scales, which evidence strongly suggests, then space could extend infinitely, with the structure repeating endlessly. This is called a spatially infinite universe, and it is the default expectation in modern cosmology. If true, the universe might go on forever in all directions. Possibility 2. Different physical conditions. Another possibility is that beyond our observable bubble, the universe might transition into regions where the density is different. Galaxy formation changed. Physics behaves differently. For example, quantum fluctuations in the early universe may have created pockets of slightly different conditions, stretched into enormous regions by inflation. If inflation went on long enough, Our observable universe may be just one patch among many, each with slightly different properties. This is called the inflationary multiverse. It's not a separate universe, just a faraway part of the same one. Possibility 3. The universe wraps around, finite but unbounded. As discussed previously, the universe could be shaped like a 3D sphere, a 3D torus, some other curved shape in higher dimensions. In such a universe, if you traveled straight ahead long enough, you'd eventually return to where you started, just as an ant on Earth's surface eventually loops around. This is one of the most counterintuitive but scientifically viable models. It means that beyond the observable universe lies our own universe, only unreachable due to expansion. No edge, no end, just continuous curvature. Possibility 4. A boundary of a larger structure. Some physicists propose something more exotic. What if our universe is like a bubble inside a much larger multiverse foam, where each bubble is a separate cosmos with its own laws of physics? In this view, our observable universe is a tiny part of one bubble. Beyond it lies the still enormous rest of our bubble universe. Beyond that might lie entirely different universes with different constants. This is speculative, but consistent with some interpretations of inflation theory. Imagine boiling water. Countless bubbles form and disappear, sometimes merging or colliding. Each bubble is its own environment with its own properties. Our universe may be similar. One bubble in a larger sea. The cosmic light horizon. Why some regions are lost forever even if we had infinite time. There are regions of space we will never observe, not because we haven't waited long enough, but because the expansion of space is accelerating. Thanks to dark energy, some galaxies are receding so quickly that their light will never reach us. They are beyond what we call the cosmic event horizon. This horizon works exactly like a black hole's event horizon, but in reverse, a black hole's horizon prevents light from escaping. The cosmic horizon prevents light from arriving. Everything beyond that horizon is permanently cut off from us. This means there are parts of the universe that we will never be able to observe. There may be entire civilizations we will never know about. There are galaxies whose light is being stretched into nothingness. This leads to a sobering realization. The observable universe shrinks in meaningful content as time passes. Galaxies slip away faster than we can study them. In the extremely distant future, our cosmic bubble will appear almost empty except for the local cluster. But for now, we live at a golden moment when the universe is still visible and full of information. Why our cosmic bubble is special, but not unique. Every observer in the universe is at the center of their observable bubble. That includes you, me, a galaxy 40 billion light-years away, and even hypothetical aliens on the other side of the cosmos. They all see a universe centered on themselves. Their horizon is not the same as ours. Their cosmic bubble overlaps with ours, but extends into regions we cannot see. This means the universe has no preferred center. Edge and middle are illusions created by observation. Space doesn't revolve around us. Our visibility does. This idea that the universe has no special center is a pillar of cosmology called the cosmological principle. It states that, on large scales, the universe looks the same everywhere. This is why looking outward is like looking into a cosmic mirror. Whatever lies beyond our horizon is likely similar to what lies within it. The big question: can anything exist beyond space itself? When people ask what is beyond the universe, they usually imagine a dark void, a bigger space, a metacosmic realm, a physical outside. But here's the important thing. Space itself is the framework in which beyond makes sense. Asking what lies beyond space is like asking what lies north of the North Pole. There is no north beyond the pole. The concept stops applying. Likewise, there is no beyond in the spatial sense. If anything exists outside our universe, it isn't outside in a way we can describe using spatial language. This is why physicists replace the question, "What lies beyond?" with a different question. What is the global shape and total extent of space-time? This is measurable, understandable, and described by real mathematics, even if the full answer remains unknown. So what do we know for sure? Here is what the evidence strongly supports. There is no scientific reason to think space ends. There is no observational hint of an actual boundary. The universe beyond our horizon likely continues. It may be infinite or simply very large. The observable universe is only a small part of the whole. The edge we talk about is actually a limit of visibility, not existence. What lies beyond? More universe, maybe with fascinating differences, maybe almost identical, maybe stranger than anything we have the tools to imagine. But it is almost certainly not nothing. Could space actually end? What if the end loops back to the beginning? Black holes, baby universes, and the multiverse debate. By now, we've established several important foundations. The universe probably doesn't end where our observations stop. The observable edge is not a real edge, just a horizon defined by light and time. Space likely continues far beyond what we can detect. Still, the original question keeps lingering in people's minds. But could space end somewhere, like a real edge? Something physical? A boundary that says, beyond this point, no more universe? It's a natural question. Humans are used to things having boundaries. Rooms have walls. Cities have city limits. Even a giant ocean has a seafloor. Why should the universe be any different? Let's explore that idea carefully. Could space end? A hard question with an uncomfortable answer. Imagine flying through space in a futuristic spacecraft, far beyond galaxies, beyond clusters, beyond anything we've ever seen. You keep going for billions of years, then trillions. Would there ever be a moment where you hit a cosmic wall? Some kind of invisible membrane? A cosmic cliff where space just stops? The short answer is probably not. The long answer is it depends entirely on the shape of space-time. To understand why, we need to break down what ending even means in cosmology. There are three major possibilities. Scenario 1. Space is infinite, no edge, goes on forever. This is the simplest scenario and the one most physicists consider likely. If the universe is spatially infinite, then it has no edge, no boundary, no limit, no outside. This is similar to asking, what's the edge of the set of all integers? It doesn't have one. You can count forever. Same with infinite space. If this is the case, then beyond the universe is mathematically meaningless because the universe is already everything. Scenario 2. Space is finite, but has no edge, like the surface of a sphere. This one is trickier but fascinating. Space could be finite but unbounded, meaning it has a limited size, but no boundary or edge. The classic analogy is Earth's surface. It's finite. But if you walk in a straight line, you never hit a wall. You eventually return to where you started. Apply this idea to 3D space. Travel straight forever. Eventually loop around. End up back where you were, without ever hitting an edge. This is a universe shaped something like a 3-sphere, a 3D torus, a more complex manifold with curvature we can't picture intuitively. In these models, space ends the way a circle ends. You can walk it forever, and it folds in on itself. This is a legitimate, mathematically accepted solution to Einstein's equations. If this were true, beyond simply loops back into the same universe. You can't escape it because the universe is all possible locations. Scenario 3. Space has an actual edge, a boundary to space-time itself. This is the least likely scenario, and also the hardest to define. To have a physical edge, space-time would need to stop existing beyond a certain coordinate, not continue in any direction past that point, have physical laws that simply end there. It would be like driving to the end of a highway and seeing a sign that says, "End of universe. Beyond here, no space-time." Physics strongly resists this idea because there's no mechanism for a boundary. Boundaries introduce unsolved paradoxes. Einstein's field equations do not naturally produce an edge. Quantum field theories break if space just cuts off. Most importantly, the universe would need a physical structure holding this edge in place. But what lies outside that edge? Nothing? Something? A metaspace? Every attempt to define such a boundary runs into contradictions. This is why cosmologists overwhelmingly reject the possibility of a real space-time edge. If space doesn't end, could the end loop back into the beginning? One of the most elegant possibilities is that the universe might be shaped in a way that, if you travel far enough, you eventually return to your starting point. You wouldn't know you were looping because space would appear flat on small scales. The curvature is extremely slight. Light would still travel straight from your perspective. Imagine playing a video game where the map wraps around. If you run far enough east, you reappear on the west side. But the game world feels seamless. Physicists call this a topologically closed universe. How would we know if this is our universe? By looking for patterns called matched circles in the cosmic microwave background, which would indicate light has wrapped around space. So far, observations haven't found strong evidence for this, but they also haven't ruled out the possibility at larger scales. It's still on the table. A universe that loops means no edge, no outside, no end, no beginning in a directional sense, just continuous geometry. This is one of the most mind-bending but scientifically valid solutions. Black holes, gateways to new universes. This is where cosmology dips into ideas that are still speculative, but grounded in actual research. Some physicists, including Lee Smolin, Nikodym Popławski, and others, propose that every black hole might be the seed of a new universe. Here's the logic. 1. A black hole collapses matter to an ultra-dense state. 2. That matter may bounce into a new region of space-time. 3. The new region expands, like a smaller Big Bang. 4. Our own universe may have formed from a black hole in a parent universe. This model is called cosmological natural selection, or the black hole cosmology model. What's wild is that this concept appears naturally in certain mathematical extensions of general relativity, including loop quantum gravity, Einstein-Harton theory, bounce cosmology models, In some versions, the singularity is replaced by a bounce. Space sprouts a new universe on the other side. The interior of a black hole isn't a dead end. It's a beginning. Think of a black hole like a cosmic seed pod. From the outside, it looks small. But inside, space may inflate into a vast universe. The connection between the two may be as tiny as the Planck scale. This is speculative, yes, but it is not science fiction. Real equations support the possibility. If true, our universe might be part of a family tree of universes. Each universe produces offspring through black holes. Universes with more black holes produce more descendants. This creates a type of cosmic evolution, universes naturally selecting for conditions that form black holes. It's one of the most creative ideas in theoretical physics. Are we one universe among billions? This brings us to the multiverse, the idea that our universe is one of many. There are multiple versions of the multiverse concept, each with different levels of scientific support. Multiverse Level 1, Infinite Universe. This is the simplest version. If space is infinite, then all possible configurations of matter occur somewhere. There are regions of space beyond our horizon that look different from our own. There may even be identical copies of Earth extremely far away. This is not speculative. It is a natural prediction of infinite space. Multiverse Level 2. Eternal inflation developed by Andre Lind and others. This model says, space underwent rapid inflation after the Big Bang. Inflation did not stop everywhere at the same time. Some regions stopped expanding and became bubble universes. Other regions continued expanding endlessly. This creates a frothy sea of universes. We live in just one bubble. Evidence? Inflation itself is supported by measurements of the cosmic microwave background. Multiverse Level 3, Many Worlds Quantum Mechanics. In this interpretation, every quantum event splits the universe. All possible outcomes exist in parallel. There are countless versions of you reading this sentence. This is not related to space ending or not ending, but it is a form of multiverse. Multiverse Level 4, Mathematical Multiverse. Proposed by Max Tegmark, this is the most abstract idea. Any universe that can exist mathematically does exist. Reality is the set of all mathematical structures. This is philosophical, not observational. What is beyond the unobservable edge? Let's return to the central question. Beyond the edge of the observable universe, there are three main possibilities. 1. More universe like ours. Same laws of physics. Same large-scale structures, just extremely far away. This is the standard expectation. 2. Regions that look very different, perhaps. Galaxies formed differently. Densities vary. Physical constants changed slightly. This comes from early universe quantum fluctuations. 3. Entirely different universes with different physics. This emerges from multiverse models. Maybe no atoms, no stars, different dimensionality, different laws of gravity. Cosmologists can't rule this out. Why we may never find a physical edge, even if one exists. Here's a crucial point. Even if the universe does have an edge, it might be impossible to observe it, because space expands faster than light at large distances. The event horizon hides regions permanently. Inflation may have pushed the edge far beyond visibility. It is entirely possible that the universe is finite, but the observable part is too small to detect its curvature or boundaries. It's like living on Earth but exploring only your backyard. You wouldn't know the planet is round. What if space is a higher dimensional shape? There's another possibility rarely discussed outside physics circles. Space might be embedded in a higher dimensional space. Imagine a 2D creature living on the surface of a sphere. They see only 2D. They don't know the sphere curves in 3D. They can't detect the embedding dimension. Likewise, our universe could be a 3D surface inside a larger dimensional reality. This is known as brain cosmology. In such models, the edge of our universe is not a spatial boundary. It is the limit of the brain itself. Other universes may exist as neighboring brains floating in a higher dimensional space. This is mathematically allowed by string theory, M theory, certain inflation models. If true, the universe may have an edge, but one we cannot leave because we are confined to the brain. You could try flying off the universe, but you would simply move along the brain forever. The higher dimension is inaccessible. This is one of the most exotic explanations for why we don't observe an edge. The big question: will we ever know the true shape of the universe? Scientists have proposed several ways to detect whether space is infinite or loops back on itself. Look for repeating patterns in the cosmic microwave background. Search for circles of matching temperature fluctuations. Detect gravitational lensing anomalies. Measure global curvature with extreme precision. Study the distribution of galaxies at the largest scales. So far, space appears extremely close to flat. No repeating patterns have been found. No evidence of boundaries has appeared. No sign of an end has been detected. But flat could still mean infinite, or so large and curved that we can't detect curvature across our observable region. The verdict? We may never know. But the search continues. Bubble universes, cosmic endings, higher dimensions, and the limits of what we can ever know. If you've made it this far, you've probably noticed something. Understanding the edge of the universe isn't just about distance. It's about understanding the nature of reality itself, how space behaves, how dimensions interact, and how cosmic structures evolve across unimaginable scales. So now, let's go deeper. Now, we are going to explore the big, dramatic possibilities. Are we living inside a cosmic bubble? Could the universe tear itself apart? What does the end of time even mean? Are we inside a simulation? Why might we never learn what lies beyond the observable edge? This is where the universe stops feeling like a place and starts feeling like a system, a structure, or a mathematical object. Let's begin with the most popular and strangely comforting idea. Are we inside a cosmic bubble? One of the most successful theories in modern cosmology is cosmic inflation. The short version: the universe expanded exponentially right after the Big Bang. But inflation might not have stopped everywhere at the same time. Some regions slowed down and became bubble universes. Other regions kept inflating forever. We live inside one of those bubbles. Not metaphorically, literally. Physicists call this eternal inflation, and it's one of the clearest explanations for why the universe looks so smooth, uniform, and structured. If this model is correct, our universe is a pocket of stability inside an endlessly expanding multiverse. Imagine boiling water. Each bubble that forms in the pot is its own separated region. Those bubbles don't merge. They remain isolated. Each bubble is a different environment with its own temperature, its own pressure, and its own internal physics. Now replace water with space-time and bubbles with universes. This is the picture inflation gives us. Inside our bubble, light travels, atoms form, stars ignite, chemistry happens, conscious life emerges. Outside the bubble, we don't know. We may never know. Light from other bubbles can't reach us because the space between bubbles expands faster than light. What lies beyond our bubble isn't just unobservable. It's fundamentally disconnected from our universe. This raises a remarkable question. If we are inside a bubble, does that mean there are other bubbles nearby? Nearby is a strange term here. Distances between universes aren't distances in any ordinary sense. They exist in separate pockets of space-time, separated by a field still undergoing exponential expansion. We can't reach them. They can't reach us. We are sealed inside our cosmic bubble forever. Will the universe tear itself apart? Spoiler, maybe, possibly. We're not sure. Astronomers have discovered something unsettling. The expansion of the universe is accelerating, not slowing down, not steady, accelerating. Something, which we call dark energy, pushes space apart more and more over time. The implications are enormous. Depending on the true nature of dark energy, one of these fates could await the universe. Scenario A. Heat death, most likely. This is the standard prediction. The universe expands forever. Galaxies drift apart. Stars burn out. Black holes evaporate. Temperature moves toward absolute zero. Nothing happens because nothing can happen. This is the quiet ending. Not dramatic, but inevitable under simple models. Scenario B. Big Rip. Terrifying but unlikely. This happens if dark energy grows stronger with time. If that's the case, galaxy clusters get pulled apart. Galaxies themselves tear. Solar systems destabilize. Planets shatter. Eventually, atoms themselves are ripped open. Everything, literally everything, is torn apart. You don't need to worry though. If the Big Rip happens, it'll be in about 22 billion years. Set a reminder. Scenario C. Big Crunch. Falling back in. This is the opposite of the Big Rip. If dark energy changes and becomes attractive instead of repulsive, or if gravity eventually overpowers expansion, the universe could slow down. Expansion could reverse. Everything collapses inward. The universe ends in a colossal implosion. This was once considered plausible. Now, current data suggests the universe won't crunch, but we haven't ruled it out. Scenario D. Big bounce, the universe recycles itself. In some theories, the universe expands, stops, reverses, collapses, bounces, expands again. This could produce infinite cycles of universes. If true, then the edge of the universe is not spatial, it's temporal. The universe ends in time, then begins again. And what lies beyond the edge of the universe? Another universe. This might be one of the most elegant answers possible. The simulation theory detour. Are we inside someone's cosmic game engine? We need to address the elephant in the digital room. Some physicists and philosophers believe our universe could be simulated. To be clear, there is zero scientific evidence that we live inside a simulation. But there are reasons thoughtful people consider the idea. 1. The universe runs on mathematical rules. This resembles computational logic. 2. The universe has a maximum speed limit, light, like a rendering limit in a simulation. 3. Quantum physics behaves like probability collapse, like a graphics engine loading only the part you're looking at. 4. The universe has a finite amount of information per volume, similar to data compression. The argument goes, if a civilization becomes advanced enough, it could simulate universes. If simulations vastly outnumber real universes, then statistically, we're probably inside one. It's an intriguing argument, but it solves nothing about the structure of the universe itself. If we are simulated, then the edge of the universe may be simply a limit of computation, a memory boundary, or an intentional design choice. But without evidence or predictive power, simulation theory remains an interesting thought experiment, not a scientific model. Observational limits, why we may never know the true shape of the universe. This is one of the most important ideas in cosmology. The universe may have features that are impossible for us to observe, not because we lack technology, because physics forbids it. Here are the big obstacles. 1. The speed of light has a speed limit. Even with infinite time, we can only see things light has had time to reach us from. This creates a permanent horizon. 2. Cosmic expansion. Beyond a certain distance, space expands faster than light. Objects there recede from us forever. We will never see them, even if they shine the brightest light imaginable. 3. Cosmic inflation. Inflation stretched space before light existed. Anything beyond that inflated region is permanently disconnected. Imagine blowing a balloon extremely fast. Points become too far apart to influence each other. That's our universe. 4. Finite time. Since the Big Bang, the universe is 13.8 billion years old, but the observable universe is about 46 billion light-years across. This mismatch alone shows how much we're missing. 5. Quantum uncertainty. The universe at the smallest scales is fundamentally unpredictable. Even perfect measurements can never reveal hidden variables, because there are none. This limits how precisely we can model the early universe. 6. Information horizons. Black holes trap information behind event horizons. The universe has its own event horizon, a cosmic one. Beyond it, information can never reach us. Events there can never affect us. Observations are fundamentally impossible, even in principle, even with infinite technology, even if humanity lives for trillions of years. Because the universe is not just large, it has regions permanently disconnected by space-time itself. This is the harsh truth. The universe may have an edge, but it may be an edge we can never reach. Could the universe have a higher dimensional shape? Now we get to one of the most mind-expanding possibilities. Our universe might be a 3D slice of a 4D shape, a membrane, brain, floating in higher dimensional space, curved in dimensions we cannot perceive. Think of a 2D creature living on a sphere. It feels its world is infinite and flat. It can't detect the curvature. It can't leave the sphere. It has no concept of up or down. We might be those creatures. We could be living inside a 3D boundary embedded in a 4D space-time. We can't step out because our physics is confined to the surface of the higher dimensional manifold. If so, the universe's edge isn't a wall. It's simply where the brain ends. But we can't fall off because the laws of physics don't allow motion in those directions. In this model, the universe could have any number of shapes: toroidal, like a donut; hyperspherical, like a 4D sphere; hyperbolic, saddle-shaped, or something stranger. These shapes define the universe's global structure, and what lies beyond those shapes is not space, but higher dimensional geometry. This is not imagination. String theory and M theory require 10 or 11 dimensions. Cosmological brain world solutions naturally arise from those theories. If these models are correct, the universe's edge is a dimensional limit, not a spatial one. So what is beyond the edge of the universe? Given everything we've explored, here are the scientifically valid possibilities. Possibility 1. More universe that we cannot see. Most likely, space simply continues. Possibility 2. The universe loops back on itself. Finite but unbounded. Possibility 3. Other bubble universes produced by eternal inflation. Possibility 4. Higher dimensional realms, we are confined to a 3D brain. Possibility 5. The edge is temporal, not spatial. The universe ends in time, not space. Possibility 6. A real edge exists, but its unreachable expansion puts it forever out of view. Possibility 7. The universe is simulated. The edge is computational, not physical. Possibility 8. The universe creates new universes through black holes. Possibility 9. The edge doesn't exist at all. Because edge is the wrong concept. Black holes, cosmic recycling, quantum limits, and why. Edges may be processes, not places. When people imagine the edge of the universe, they often picture something physical. A wall, a cliff, a border, a hard stop. But physics suggests something very different. If the universe has an edge at all, it might be found not out in the distance, but in the places where the known laws of physics fail. And nothing stretches those laws to breaking like black holes. Black holes, where space and time stop making sense. Black holes are not just intense objects, they're the most extreme locations in the universe, places where gravity becomes infinite, space folds in on itself, time slows to a crawl. The known laws of physics break. This makes black holes an obvious candidate for the question: could something beyond the universe lie inside them? Surprisingly, some of the smartest physicists think the answer might be yes. Are black holes gateways to new universes? A black hole has two key features. 1. Event horizon, the surface beyond which no information returns. 2. Singularity, maybe, a point of infinite density where space and time collapse. But here's the twist. Physicists increasingly believe that singularities, literal infinities, probably don't exist. Instead, they may be placeholders for new physics we haven't discovered yet. This opens the door to bold ideas. Possibility 1. A black hole forms a bounce matter. Collapsing could reach an incredibly high density, then rebound into a new expanding region of space-time. A baby universe. Possibility 2. Black holes connect to other universes. The other side of a black hole might be a white hole, a region where matter explodes outward rather than collapsing inward. Possibility 3. Our universe was born from a black hole. This sounds like sci-fi, but it's a legitimate hypothesis published by respected physicists. In this view, a black hole forms in some parent universe. Its core rebounds. That rebound becomes a Big Bang. A new universe forms inside our universe could literally be the interior of a black hole in another universe, which raises a stunning possibility. Every black hole in our universe may be a seed of a new universe. This is a real research program, known as cosmological natural selection. It suggests universes evolve like organisms. Black holes reproduce universes with slightly different physical constants. if so, the edge of our universe lies inside a black hole in another universe. And inside our black holes lie the seeds of future universes. Edges begin to feel less like boundaries and more like birth canals. The universe may recycle itself. We traditionally imagine the universe as a singular event, a beginning, an evolution, an end. But many modern models paint a more interesting picture. The universe may recycle itself. Let's explore the family of bounce theories. 1. The Big Bounce Loop Quantum Cosmology. Quantum gravity models describe space-time as granular, a fabric woven from tiny loops. When the universe contracts, these loops resist further compression and prevent a singularity. Instead, the universe bounces and begins expanding again. Meaning, before our Big Bang, there was a prior universe. Before that universe, another, and so on cycles continue indefinitely. Here, the edge of the universe is simply the moment of transition between contraction and expansion. 2. Ekpyrotic universe, brane collisions. In this model, our universe is a 3D brane floating in higher dimensional space. Another brane exists parallel to ours. Every so often, the two branes collide. Each collision releases enormous energy, triggering a Big Bang. This avoids singularities and explains cosmic uniformity. The edge of our universe is not a location. It's an event in higher dimensional space. 3. Conformal cyclic cosmology, CCC, proposed by Sir Roger Penrose, a Nobel Prize winner. In CCC, universes don't bounce. Instead, they fade out as expansion becomes infinite. The far future becomes indistinguishable from the Big Bang of the next universe. It's like a cosmic Ouroboros. Universes birthing universes in an endless chain. Penrose even claims evidence may exist inside the cosmic microwave background of our universe, showing circular patterns from a previous universe's black holes. Whether the evidence holds is debated, but the theory is elegant. Could the universe be a shape we can't visualize? We are three-dimensional creatures trying to understand a system that might be fundamentally higher dimensional. This is like a goldfish trying to understand the plumbing behind its aquarium. Mathematicians can describe shapes we cannot imagine. 4D spheres, 5D toruses, hypercubes, Calabi-Yau manifolds, non-Euclidean geometries, topological defects. The universe could be finite but unbounded because it is embedded in a higher dimensional structure. For instance, a hypersphere. You can travel in any direction forever and never reach an edge. You come back around to your starting point. A 4D torus space loops in multiple dimensions simultaneously. If the universe has a topology like this, the edge is not a physical boundary. It is the limit of perception, the structure of space-time, a shape our minds can't fully picture. This isn't speculation. Topology is a standard part of cosmology. NASA and the ESA have both searched for repeated patterns in the cosmic background that would indicate a looping universe. No conclusive evidence yet, but no contradiction either. Quantum limits. Why some answers may be unknowable. Even with infinite technology, some properties of the universe might be permanently inaccessible. Here's why. 1. The cosmic horizon is uncrossable space expands faster than light beyond a certain distance. No ship, no signal, no technology can ever reach those regions. Those regions may contain the shape of the universe, evidence of other universes, the true global curvature, clues to the early universe, but they're beyond reach forever. 2. Quantum uncertainty locks away information. Quantum mechanics prevents infinite precision. This means we can never fully know the exact state of the early universe, what happened at t0, the exact shape of spacetime at the smallest scales. There are built-in limits to knowledge. 3. Black holes hide information. Black holes have event horizons. They trap information in ways we still don't understand. If universes are born inside black holes, then the history of those universes may be permanently sealed. We may be living inside a universe whose own origin information is locked away in a black hole in a parent universe. 4. Inflation wipes out initial conditions. Inflation erased all information about what came before it. It smoothed out density variations, initial geometry, early fluctuations. The universe looks uniform because inflation ironed over its past. This means the true initial state of the universe is unknowable. Maybe the universe has no edge, because edges don't make sense at cosmic scales. Consider again the idea of an edge. Edges are human constructs, things that we evolved to understand. Cliffs, doors, walls, boundaries, containers. But the universe is not an object inside something larger. It is the thing. All of space, all of time, all of causality. Asking, where is the edge, is like asking, what's north of the North Pole? What's outside of space? What's earlier than time? Sometimes the problem is the question, not the answer. The universe may have no edge because edges require an outside. The universe has no outside. As we move deeper into the question of what might lie beyond the universe, it becomes clear that we are not only wrestling with physics, we are wrestling with human intuition itself. Nearly every mystery surrounding the edge of the universe comes from a simple truth. Our brains didn't evolve to understand cosmic scale. They are built for finding fruit, avoiding the cliffs, and recognizing faces. Not for conceptualizing curved space-time, eternal inflation, or higher dimensional topology. This mismatch between intuition and reality is not a flaw. It's a starting point. Humans ask questions about edges because we're wired to think in boundaries. Every experience we have is bounded. The sky ends at the horizon. Oceans end at shorelines. Rooms end at walls. So the idea of a universe without edges feels incomplete, like an unfinished sentence. When physicists explain the universe has no edge, the human mind instinctively searches for a loophole. Okay, but what's it expanding into? What's outside? What came before? We ask because we biologically default to finite containers. But physics consistently answers back with something stranger. The universe may not be inside anything. It might not need an outside. Space could be self-contained, like the surface of a sphere, finite but without boundaries. Time might not extend infinitely backward. Even causality might break near the earliest moments. And if we live in a multiverse, our universe could be just one pocket among many, all floating in a vast, unobservable domain where edges lose all meaning. The question is not merely scientific, it's emotional. People want edges because edges provide orientation. Knowing the shape of our surroundings helps us understand where we are. In everyday life, you know the edge of your city, the edge of your property, even the edge of your phone screen. If the universe lacks those landmarks, what does that imply about our place in it? There's a subtle discomfort in realizing that the universe may be boundless, or that we may never know its true shape. Yet there's also something profoundly freeing about it. When boundaries disappear, so does confinement. The universe becomes a canvas larger than imagination itself, where our curiosity roams without fences. Still, curiosity isn't satisfied by philosophy alone. We want measurements, observations, data points, evidence. And that brings us to one of the most important ideas in cosmology: observational limits. The idea that even with the best technology imaginable, our view of the universe is fundamentally restricted. Not by engineering, not by effort, but by the laws of physics. For example, the speed of light sets a hard limit on how far back we can see. The expansion of space pushes regions of the universe away from us faster than light can travel. Those regions fall permanently beyond our horizon. Even with infinite patience, infinite telescopes, and infinite computational power, we cannot reach them. Many cosmologists believe these unreachable regions contain answers to the universe's global shape, geometry, and topology. But nature has placed a fog, a cosmic privacy curtain, preventing us from ever looking beyond. This raises an unexpected and rather humbling question. If the universe contains truths we cannot observe, what does that say about the nature of science? For centuries, science has operated on the assumption that with enough time and ingenuity, all mysteries eventually yield to human inquiry. But cosmology might be the first field to confront a permanent barrier. Some answers might not be hidden. They might be unobservable by definition. Still, science adapts. When direct observation fails, theory steps in. Not to invent fantasy, but to build logical structures consistent with everything we can observe. For instance, inflation theory was proposed long before we could see its consequences. Later, evidence in the cosmic microwave background strongly supported the theory. Similarly, the multiverse isn't a wild imaginative leap. It emerges naturally from well-tested equations in inflationary physics. This brings us back to the idea that the universe may not be the whole story. If inflation is eternal, new universes could form endlessly in a vast cosmic foam. Our universe becomes just one bubble among countless others. And if that's true, the word edge shifts meaning entirely. Instead of thinking about a boundary around our universe, we think of transitions, places where new universes branch off, places where inflating space buds into new bubbles. Instead of a wall, the edge becomes a process, a mechanism by which universes proliferate. Of course, none of this is directly observable, not because it's unscientific, but because the physics places natural limitations on access. If another universe lies beyond ours, we may never see it. It might be separated from us by inflating space expanding faster than light. It might be governed by different physical constants. It might be as unreachable as yesterday. And yet, the notion persists because the mathematics demands extensions beyond our observable region. Theories that stop abruptly at the limits of what we can see tend to be unfaithful to their own internal logic. Physics doesn't like arbitrary edges. If something happens here, and the equations still work everywhere else, then everywhere else must include regions we can't observe. Thus, many cosmologists consider the multiverse a natural consequence of the physics we already understand. But let's pull away from these vast theoretical spaces and return to something more grounded, what the question reveals about us. For decades, the question, what lies beyond the edge of the universe, has persisted not because science hasn't answered it, but because the answers challenge human expectations. People aren't satisfied with "there is no edge," because that response contradicts centuries of intuitive thinking. We want something firmer, a barrier, a boundary, a frontier. We want the universe to be a place we can draw a map of, even if it's gigantic. Consider how our ancestors viewed the world. Before global travel, many societies believed the Earth had an edge. Beyond the ocean lay monsters, waterfalls, or emptiness. Over time, evidence replaced myth. The Earth revealed no boundary. It curved. The horizon was not an edge, but a limit of perception. That same transformation may be happening again at a cosmic scale. The edge of the universe might not be a place, but a horizon created by perspective. Our cosmic horizon is just like the sea horizon, a boundary defined by our limited position, not by the universe itself. Someone else, far away, would see a different horizon. There is no single boundary that marks where the universe stops. But this raises a delightful philosophical twist. Even though we can't see beyond our horizon, objects exist there. Galaxies, stars, clusters, all continuing out into regions forever hidden from us. If the universe has an edge, it certainly isn't one we can see from within. Now, here's where the human perspective returns. People often ask these questions not purely out of scientific interest, but because it helps them locate themselves in the grand tapestry of existence. Understanding the universe's shape, size, and boundaries isn't just physics, it's existential orientation. It's the modern version of where do we fit? That's why the edge question touches something deeper. It's really asking, how far does the world extend beyond us? How small are we? How much more is there to know? Are we part of something contained or something infinite? Are we in a universe that began once or one in constant renewal? Questions about the edge become questions about belonging. Am I living in a confined bubble, or am I floating through an endless expanse? The fact that science leans toward the second answer can be overwhelming or exhilarating depending on temperament. Some people find comfort in the idea of an infinite universe, a reality so large it dissolves boundaries. Others prefer a universe with a clear beginning, middle, and end, something structured. Science doesn't cater to preference. It follows evidence wherever it leads. And so far, that evidence suggests the universe is not only stranger than we imagine, it may be stranger than we can imagine. Concepts like unbounded space, eternal inflation, multiple dimensions, quantum limits, cosmic horizons. These aren't exotic sideshows. They're mainstream physics. The very fact that space is expanding everywhere simultaneously suggests something profound. The universe might not be expanding into anything. Space itself is stretching. Galaxies aren't flying through space. New space is forming between them. No edges emerge from this picture. Space doesn't reach a boundary and stop. It simply keeps unfolding. But will we ever truly know? That's the core of the question. Will humanity ever break through the observational limits and uncover something that reveals the universe's large-scale structure? Will technology one day surpass barriers that currently seem absolute? Or will the laws of physics permanently prevent us from seeing beyond our cosmic horizon? Physicists are split. Some believe new breakthroughs in quantum gravity could one day clarify the true shape of the universe. Others argue that the observable universe may be the only part of reality we can ever access, and everything beyond will remain a domain for theoretical inference. We face an irony. The more we understand the universe, the more it reveals boundaries in our ability to know. Yet that doesn't diminish the power of the question. Humanity's progress has always been driven by curiosity, even when the answers lied beyond the horizon. Exploration doesn't require guaranteed outcome. It only requires wonder. And few questions inspire more wonder than what lies beyond everything we can see. If the universe has no edge, then our questions become boundless. If it does have an edge, finding it would transform physics forever. Either way, the pursuit expands human understanding. The closer we come to the end of this long journey, ironically, a journey about things that may not have an end at all, the more natural it becomes to ask what we are actually pursuing. Are we trying to locate the physical boundary of the universe? Or are we trying to understand the boundary of our own comprehension? Because at this point, after crossing through the early universe, cosmic horizons, inflationary bubbles, higher dimensions, and the possibility of an infinite multiverse, the question, what's beyond the edge of the universe, has become less about astronomy and more about the outer frontier of what a human brain can comfortably process. When scientists debate what lies beyond the observable universe, they aren't only discussing physics, they're also dealing with the constraints of measurement, perception, and the nature of inquiry itself. They're trying to figure out what kinds of truths are accessible to beings who evolved to survive on a single small planet, never designed to contemplate the geometry of the cosmos. Yet, somehow, here we are, using equations, satellites, and a lot of caffeine to peer into the structure of reality. One of the most important realizations in all of cosmology is that the observable universe is not the universe, just the part we can currently access. That subtle difference in wording carries enormous implications. The observable universe is a sphere defined not by the universe's boundaries, but by the limits of light travel and cosmic expansion. Every year, that sphere grows, not because the universe is expanding into something, but because more light reaches us from previously unobservable regions. Like turning on a lamp in a dark room, except the room itself keeps growing while you're trying to illuminate it. But even this growth has a ceiling. Beyond a certain distance, space expands faster than light can cross. This creates a barrier, not a physical wall, but a constantly shifting, receding horizon. No matter how advanced our technology becomes, no telescope can overcome that boundary. It is not an engineering challenge. It is a structural feature of space-time itself. This is where the universe behaves in a way that contradicts every instinct we have. Human intuition prefers clear edges, cliffs, borders, outlines. Cosmology, on the other hand, gives us moving targets, infinite expansions, and horizons that recede faster than we can chase them. The universe doesn't offer the comfort of a neatly drawn map. Instead, it gives us a dynamic, evolving arena where visibility is limited, and the unseen massively outweighs the seen. That's partly why speculative models, like the multiverse, higher dimensional space, cosmic bubbles, and cyclical universes, are taken seriously by physicists. Not because they are low-effort explanations, but because the parts of the universe we can observe already suggest a reality that is far larger than our observational reach. These models attempt to extend our understanding beyond our horizon, using equations and evidence we do have. They offer conceptual scaffolding, bridging the gap between the observable region and the possible whole. Take the eternal inflation model. It proposes that inflation, the rapid expansion that shaped the early universe, never fully stopped. Instead, pockets of space continually exit the inflationary phase, creating bubble universes, each with its own physical laws. If that idea is correct, our universe is just one of many, floating like a single bubble in an infinite froth. In that scenario, the phrase edge of the universe stops referring to a border and instead refers to a boundary of our bubble, beyond which lie other bubbles forever disconnected from our own. But eternal inflation is not the only model pointing beyond our observable domain. Certain versions of string theory predict that our universe might be confined to a three-dimensional brane, floating within a higher dimensional space. In this picture, the edge of the universe may not be a place but an interface, where our brain exists within something larger. Other brains might exist parallel to ours, separated by microscopic gaps in additional dimensions. And if such models are correct, the true nature of the universe is not merely vast, but fundamentally layered in ways we cannot detect with present-day technology. This brings us back to one unavoidable point. Even with the most powerful tools, some aspects of the universe remain permanently beyond our reach. And that's not defeatist. It's a scientifically mature recognition. In physics, as in life, not all unanswered questions imply failure. Some simply point to deeper levels of understanding that require new frameworks. A century ago, people thought the Milky Way was the entire universe. Today, we know it is one galaxy among trillions. We thought space was static. Now we know it expands. We thought time flowed uniformly. Relativity proved otherwise. We thought empty space contained nothing. Quantum physics filled it with fields, fluctuations, and potential energy. Every time we believed we had reached the limit, the universe expanded the definition of limit. This pattern suggests that our current horizon, what we can see and measure, is likely not the final boundary of understanding. Future generations may develop new technologies, new mathematical tools, or new physical theories that allow them to infer things about beyond-the-horizon regions indirectly. Already, cosmologists infer the shape of global spacetime using patterns in the cosmic microwave background. We deduce the existence of dark matter from the way galaxies rotate. We infer dark energy from accelerating expansion. Perhaps future discoveries will allow similar inference about what lies beyond our cosmic bubble. But even if we never observe those regions directly, that doesn't diminish the value of the question. In fact, the pursuit itself may be the point. The edge of the universe represents the ultimate intellectual horizon, a reminder that our understanding is always incomplete, always reaching, always stretching outward. And here's the twist, that endless pursuit is a feature, not a flaw, of scientific thinking. Certainty is comfortable, but progress rarely grows out of comfort. It grows from questions we can't yet answer. The universe doesn't give us edges, so we build conceptual ones, horizons, models, mathematical boundaries. They help us explore the unknown, but they also remind us of our perspective. From inside the universe, trying to see outside may be like a character in a story trying to read the book therein. The very structure that defines existence also defines what can be known. So, what actually lies beyond the observable universe? The most honest answer is something real but not accessible. Whether that something is more of the same galaxies, or radically different physics, or bubble universes, or higher dimensions, or a repeating cosmic cycle, remains an open question. And it might stay open forever. Yet, there is a strange comfort in that. The unknown isn't just a gap in understanding, it's also an invitation. It keeps curiosity alive. It keeps science moving. It gives each generation something meaningful to wrestle with. If the universe had a simple wall at the edge, painted with a cosmic "stop here," the mystery would end. And with it, much of the inspiration that drives exploration. Instead, we have a universe that keeps the biggest secrets just out of reach, not to frustrate us, but to keep the process alive. Humans climbed mountains because they were hard. They crossed oceans because they were vast. They look into space because it stretches farther than imagination. The edge of the universe is not a place we find. It's a horizon that moves with us, always reminding us that discovery is an ongoing story. So, whether the universe is infinite or finite, whether it contains one cosmos or many, whether space wraps around itself or extends endlessly, whether dimensions hide beyond our perception, or everything we see is all that exists, the pursuit itself has value. Asking what lies beyond the edge keeps us connected to the same curiosity that fueled every scientific breakthrough in history. Perhaps the universe's greatest gift is that it always leaves room for more questions. And maybe that's the true answer to what lies beyond the edge. Not a frontier of space, but a frontier of understanding. One that will never fully close.